What is artificial intelligence? If you want to find out what it is, in this video we talk to Larkin, the data scientist, and discover what it is.
Hey guys, I'm Najeeb Khan. I'm an author, I'm an award-winning entrepreneur, and an innovation strategist. And in this channel, you're gonna find everything you want to learn about innovation, design, and creativity.
Hey guys, I'm here with Larkin Liu. He's the data scientist at StackAdapt. And we're going to be talking a bit about data science, machine learning, and creativity, as well as artificial intelligence. So, obviously we chatted a bit earlier. Could you explain a bit more about where you see, or very blanket question, what is AI in your point of view?
Okay, before I begin talking about this, my background is more in applied math and operations research. So I look at artificial intelligence from that perspective. But
a bit louder.
Yeah, artificial intelligence from that perspective. But there is very strong overlap between applied mathematics, applied statistics, and artificial intelligence. So before I talk about artificial intelligence, let's distinguish between artificial intelligence and artificial general intelligence. I think most people think of AI, they think of AGI, which is this humanoid, like Iron Man, Jarvis,
right?
This, HAL 2001: Space Odyssey, this type of AI, where the artificial intelligence actually replaces the a human, and it's self-aware and sentient. To be honest, in my opinion, and in the opinions of many researchers as today, I mean, our level, having reached that AGI, is still very far away. And what AI is essentially is, at this point, artificial intelligence is top of the line, state-of-the-art AI right now. We're talking about self-driving cars. We're talking about algorithms that can beat humans in the game of Go or chess. We're talking about classifiers, very strong classifiers that will be able to, distinguish, as mentioned in the previous presentation, cats from non-cats, but very robustly so. And then, and machine translation and topic modeling, also very big. Right now, the cutting edge research in AI has been sort of these areas of topics. And others, of course, I may have forgotten to touch on those. So, still very far away from that AGI, artificial general intelligence, where it replaces human thinking and function, but AI is essentially doing a lot of classification and decision making. That's basically what. So, for example, on your phone, if you type a sentence, it can tell you what words you'll use after with very strong likelihood, or translate for you something from Chinese to English very accurately and efficiently with very little grammatical mistakes. And so
that is AGI.
That is artificial intelligence.
I see.
AI as of today. AGI is when you're thinking like artificial general intelligence, where like you have a human replacement of a computer. A computer replaces a human. They can actually be sentient, have intelligent conversations with you, having human characteristics given to a computer, which may or may not be possible in the foreseeable future. But as of now, AI is still primitive. But what it does best, as mentioned by Vitaly in the previous presentation, is that it scales very high, which is exactly right when he said a 5-year-old can probably identify cats better than a computer can, the best AI computer. But a 5-year-old cannot go and identify 5 million photos of cats, whereas a computer can. If they can do it with only a very small false positive rate, that's much better because it can scale. It's a strength that you give. And also, for example, in self-driving cars, like computers, I'm sure a professional driver can still drive better than a self-driving car as of now. But self-driving car never gets tired. It can always keep going, and its reaction times are fundamentally faster. So and eventually, self-driving cars will eventually overtake because it doesn't. because eventually what driving is essentially a mechanical response to to your surroundings, and computers have so much. We only have 2D planar vision and some audio input that help us with driving, and then we have to transmit our signals to our hands and feet. But a computer can actually have direct access to the throttle, direct access to the brake, direct access to the steering, control the RPM of the wheel itself in response to the actual input that they get. And so that sensory and the magnitude of data, that's what AI is going to be able to. I think very soon, self-driving cars will be way better than human cars. But as far as humans, AI making decisions, creative decisions, this may take some more time to ramp up because for example, when recent episode, where AI has been shown to be very effective, was when AlphaGo beat the current world champion in Go,
right?
Game of Go. But one of the responses from the world's top Go player, some Korean guy, I don't know what his name was, was that the computer never got tired, and the fact that he got tired destroyed his thinking. So fatigue and sensory information, computers can do a lot more of that. But
especially if you relate that to driving, like if you look at long drives, people will just naturally get tired, especially if you're doing like an overnighter.
Yeah. So computers don't get tired, and they can take lots of data, and they can react faster. And so this is where this AI is better than humans. But as far as coming up with nouveau intelligent solutions, it's pretty good at this point, but still, everything is still within the feature space that we provide. So for machine translation, for example, before, and please don't quote me on this, because I'm not an NLP expert, I'm not a natural language processing expert. As I understand, back in the day, machine translation was you hard code a bunch of rules. This word is dictionary to that word into one word translation. Then we have hard coded grammatical rules. But as you can see, language is so complex that hard coding like a million rules is always an exception to some rules. The translation always work out like a little bit bad.
Right.
But now, I think now the new approach to translation is that we don't hard code any rules in there anymore. We just take, for example, War and Peace in Russian, the original text, then the human translated English version, then the Chinese version, and we have a one-to-one mapping of all the words. And so it sort of creates a model for the linking of words and word structures, but without any grammatical understanding of the language whatsoever. So this has shown experimentally to be more powerful than the traditional approach. Another way of thinking I've changed, for example, when Deep Blue beat, I think, Garry Kasparov in chess, the whole Deep Blue algorithm was a search. It was a search over, searching over all the possible moves that we can make, and with some smart pruning, of course. Sometimes, let's say if you go knight to b6, it's going to get taken. So then all those moves after that we don't need to do. We don't need to compute. So it's just to search over all the possible moves and find the most optimal move and move accordingly. And it keeps searching trees. The problem with Go is that the branching factor in Go was just way too massive. You can't, calculate even like 2-3 moves in advance because there's 64 by 64 spots on the Go board, and the branching factors got too huge. And memory just got used up. So they did another more probabilistic approach where they had, it was some deep learning where they took previous games that were played and find some statistical relationship between them. I'm not an expert to quote on this because I don't research in this field specifically.
Sure.
But my point is that the fundamental approach went from searching to most optimal moves to learning from previous games, and then they actually did something cool, which was they actually had the computer play against each other and create new games which they can learn from. So this approach, some people call it reinforcement learning or machine learning approach, which was based on a lot of statistical principles, is a new approach of AI. But as far as is AI AGI yet, where you can have HAL 2000 and
Jarvis
and stuff like this, it's still or like Star Trek that robot. It's still relatively far off, but not too far in the foreseeable future because that's it pretty soon. So I can only comment on what we have right now and what we don't have right now, but I cannot say maybe in 50 years we're gonna get that very powerful AGI.
So which industries do you see leveraging these type of AI or even close to AGI, or which industry do you foresee going in, branching out into AGI first?
So anything that has to do with, and then there's already a lot of companies that already want to build that AGI. For example, like bots. When you go on a website trying to purchase a car, trying to purchase,
like Facebook
you go on
bots
our
and
website,
whatnot.
there are bots that try to answer you, try to communicate with you. And even the first early chat bots have always been existent, but they're really bad AGIs. They couldn't really have any intelligent conversation. Siri is an attempt to make an AGI, but still, it's very limited in what can and cannot respond. It cannot have an intelligent conversation with you. But so these AGIs are very primitive, and there is a research department, the research effort going on to make very very good AGIs. But this is more of a UI UX, like a sort of user experience sort of thing. Don't worry about, can I communicate with the computer? Can I do this? AI researchers are focused on metrics. Can I classify? Can I bring down from, I classify 1 million images of cats, I get 10 false positives. Can I make it 5 false positives? So this is what AI research is all about, making classification better. And then, so if I put a camera in a car, can I identify pedestrians? Can I reduce the risk of accident? This is what AI research is about. And then the UX side of the user experience side, focus on making chatbots, making semantic robots that can communicate well. These two areas will eventually, merge into one AI. But when we talk about artificial intelligence and machine learning, as I understand, and I am just standing outside from my sort of applied math background.
Sure.
It's a little bit of a misconception in the general public.
Right.
Because as far as I'm aware about what AI is out there is basically, can we classify better? Can we not hit people on roads better?
So speaking of that, like something like it is, it's kind of like the ethical debate, which is if you have a car and there's a passenger inside and perhaps someone just jumps right in, something like that where you're looking at ethic is like, do you save the passenger or do you save the pedestrian? Is that something that's right now it seems like it's based off a decision tree? Do you foresee that being into an AGI?
I don't know what's based on right now. It's probably some computer vision algorithm. I don't know, decision tree maybe. Again, maybe from a strictly mathematical side, there would be no ethical component involved. It would be an optimization over, it would be a assigned loss function. If the passenger died, do we get loss of this value? And then if the pedestrian, there's be a loss of that value. And then they'll compute the optimization and then make the decision in a matter of split seconds. The computer has no understanding of what the ethical code is. It will make a decision based on what is the loss function, to minimize the loss function or maximize the objective function.
For sure.
It will just do something like that. So if you value so it will make the decision. And then of course there's probabilistic factoring in. For example, the probability of turning right and getting an accident is this percentage, and the probability of turning left and getting an accident is a lower percentage.
Sure.
But then the loss functions are different. If I get an accident on the left side, it's going to be costing me more.
Right.
Getting an accident on the right side has to do the optimization.
I see.
So that's how it optimizes, right? There's going to be a deterministic element where we assign, characteristic. We assign, the actual loss functions. I get an accident on the right side, I lose this many points.
Right.
I get an accident on the left side, I lose 5 points, I lose 4 points, but if the probability of me getting an accident may be less on the left side.
Right.
So then A, we compute the probabilities of things, left and right. What is probability of getting it? B, you assign the loss function. If 2 people
Right.
there, you can crash, and 1 person there, then that's our loss function right there.
Right.
So
one final question: what are you most excited about where this industry and technology is going?
Well, for the work that I do at StackAdapt right now, it has nothing to do with cars. I really like cars, so I sort of talk about it. And I try to see what machine learning has to do. It is actually a big field application. What I do is apply machine learning models, or I call it statistical learning models. The reason is because these models have been around for a long time. It's just that the ways that we're computing, compute parameters have changed. So back then, like I mentioned previously before, we could logistic regression, which is just machine learning researchers or computer scientists like to call it a machine learning method, but really it isn't. It's been around almost 200 years ago. was just that back in the day, you solve parameters by analytically analyzing the situation and you provide a solution on paper, a theoretical solution on paper. Now, we really don't need to. We have theory to compute 1 million coefficients, 1 million parameters, using computational methods. Because the computers, we just keep trying things and then trying different permutations and adjust the coefficient and move some gradient descent. We change the parameters and we adjust them properly. So we find the model that gives us the maximum likelihood. And so now we can apply models that were invented 200 years ago, 50 years ago, 30 years ago, but we can scale it up to 1 million parameters with like 100 million features.
Right. Exponential processing.
Yeah. And it has shown that the theory that these statisticians came up with 150, 200 years ago have shown to be very effective because the theory was there. The theory was there. It has shown to be very effective when now the computational methods are there to classify things. Because computer science, computer statistics all along. Computer science was a separate branch. Computer scientists back in the day like to back in the day, I mean the 20, 30 years ago, like to write a list of rules and then have logical reasoning about the rules, constraint programming, I think it was called. And I'm no expert in this field, but they basically write a set of rules and reason about this rule. If I turn right, then we crash 2 people. If I turn left, we crash 1 person. And we do this. But there was not a probabilistic element of that. It was just a hard set of rules, and we sort of reason about it. Now, there's a very strong probabilistic element. We compute, probabilities of going to the right. What's the probability of doing this? What's the probability of that? We compute optimal decisions. We compute. Let's say, for what I do is I compute. Let's say if you visited certain websites, we compute, the probability of you engaging with the content and clicking through the ad, and I get information like, are you from Canada? Are you from Toronto? Are you using a OS X? Are you using Mac OS X?
Sure.
Are you what's the height and width of the advertisement you're seeing? What's the content of it? What user segment you belong to? All this information I have, and we have at least 700 of these features, and we have 10 million observations a day. So I can crunch all these numbers, and I use a very basic statistical model that was invented 150 years ago. And I use another one called Random Forest, which is it's also 20, 30 years ago, a collection of decision trees, and we can predict with strong probability whether you will engage or not. Now, this is the probabilistic, the prediction element has been presented. Just like I predict a turn right, the probability of collision, and turn left, the probability of collision.
Right.
Now I predict the probability of engagement on the advertisement. Now we have formulas to set how much are you going to pay for this ad. So obviously, if we predict that you're more likely to engage, we get paid more for it. If you're less likely, you pay less for it. So we make that optimization based on that probabilistic element.
Love that.
Yeah, that's basically the shift. And I think we're not the only ones doing this. Everybody's doing this right now. There's probabilistic shifts. So I think scaling is the main component in machine learning.
And it seems like scaling is only possible once you build the system that allows you to, one, understand what it is and then completely scale.
Yeah. So computational methods have changed. 2 things have changed. One was the sort of hardware. Hardware has gotten better and better.
Right.
Microchips have gotten smaller, more transistors, more silicones. And then the algorithms to compute things, like we use MapReduce, Spark now. These algorithms allow us to compute large data sets with ease now. Sorting, aggregation, all these things can compute with ease, and we can generate parameters for models easily now. Over 1 million, 10 million data observations a day, no problem. It's pretty standard. Whereas back in the day, you would have some to wait, back in the day when you work in 1970s with your Fortran machine or whatever, you're gonna wait 2 days to get your result for some matrix maximization algorithm you're trying to run. So the theory was there, but you just couldn't compute it. And that's why something like artificial neural networks was not popular back in the day, because it wasn't very computable. It took too long to compute things. Now it takes shorter time. We can leverage that computing power. That's the main shift.
Love it.
And so I think the wrap-up point is that I don't use crazy, super advanced algorithms. Whatever I use, I'm not a very high-level researcher. Whatever I use is pretty established in the past. It's been written down in papers. People have done research on it. The tools are there. Now we just massage our data to fit into these models. And then because we can scale it up so high, that the analogy is that that it can be better than a professional driver because we have direct control over all the little fine tuning. We have the sensory is so much better. The computer can see all around it itself, and it can have full access to the throttle and brake and controlling every wheel. But a human cannot, do that, even though he might be a better decision maker.
Right.
And then so on advertising, for example, human may be the best guy to look at all the information and say this guy is much more likely to engage with the advertisement. Know your basketball player, and this is for a basketball advertisement.
Right.
But he cannot look at 10 million of these a day and then tell you that. But a computer can do that. So that is what.
Love it. Larkin, thank you so much. Really appreciate it. I hope you enjoyed it. I learned a lot. Thanks so much for your time.